So this next section is about absolute versus conditional convergence. And this is almost just a vocabulary lesson. There's not much new to this section. So my goal for you is to be able to determine whether a series converges or diverges, like it has been all chapter. And there's a little bit of new language. You might see, does this series converge conditionally? A series converges conditionally if the only reason it converges is because it's an alternating series. Other tests will show that the series diverges, but if you use the alternating series test, it converges. I guess what I mean is if you have the absolute value of all of your terms, they would diverge. So right now, this series that's written here would be the alternating series starting with -1 and then plus 1 over the cube root of 4 minus 1 over the cube root of 9 plus 1 over the cube root of 16. And this series definitely converges. It converges because the alternating series test, if I do the first part of the alternating series test, I take the limit as n goes to infinity of -1 to the n over n to the 2/3. Well, if n is going to infinity, I'm going to have a small number over a really big number. So this goes to 0. And then the other part of the alternating series test, if I look at the next term, that would definitely be smaller than the current term because the denominator would be smaller. So it passes the alternating series test. It converges as it is written. But if it were not alternating, if it were just 1 over the cube root of n squared, that series is not alternating. It's the same series except that it's not alternating, so this would be 1 plus the cube root of 4 plus the cube root of 9, etc. But this series diverges by the p-series test because p is equal to 2/3. And so we have the alternating series converges, but if it's the same series but not alternating, it diverges. And so this series is conditionally convergent. In other words, the only reason it converges is because it's alternating. If it were not alternating, it would diverge. The other option, there are actually two other options. One is that it diverges either way. So an example of one that diverges either way would be 1 minus 1, that famous one that we talked about before. So this one diverges either way. That's a divergent series. This one is a conditionally convergent series. And then the other option is absolutely convergent, and that means that it would converge even if it weren't an alternating series. So this series converges absolutely, is my claim. And so the way we're going to satisfy that claim is we're going to do the ratio test because I see a factorial. And I'm going to do the ratio test, but I'm going to do the absolute value of the terms. So when I do the absolute value of the terms, that -1 to the n just becomes 1, right? So I'm going to look at 1 over n plus 1 factorial over 1 over n factorial. And if I make that simpler by multiplying by the reciprocal, and I don't need absolute value bars anymore because everything is already positive, I'm going to have 1 over n plus 1 factorial times n factorial, and then the factorials cancel, so I wind up with 1 over n plus 1, and that limit is 0, which is less than 1. So by the ratio test, this series converges, and it not only converges, so this series with positive terms converges, so this series here is said to converge absolutely. It converges whether you slap absolute value bars around it or not. It's going to converge if it is alternating, and it will also converge if it is not alternating. If you can show that a series converges absolutely, then the alternating series would also converge. Because again, it's easier for an alternating series to converge. So that is conditional versus absolute convergence. Conditional convergence, you need to have alternating signs. Absolute convergence, this series would converge whether the signs were alternating or not. All right, thank you so much. Bye.